Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're looking at another problem on thermodynamics. This is from UNSW, and it's a problem that may seem complicated at first, but as soon as we start, dismantling it into its pieces, becomes straightforward. Okay, this problem reads like so. The space above the water in a closed tank contains nitrogen at 25 degrees Celsius and 100 kilopascals. The tank has a total volume of 4 meters cubed and contains 500 kilograms of water at 25 degrees Celsius. An additional 500 kilograms of water is now slowly forced into the tank. It can be assumed that the temperature remains constant during the compression process. Calculate the final pressure of the nitrogen and the work done during this process. Determine also the change in internal energy of the gas and the heat transferred. So let's analyze this. The space above the water in a closed tank container contains nitrogen. So the space above the water, right? So let's imagine a cup with water. The air on top of it, that's what they're talking about, right? But it's a closed container, so it's a cup that has a lid. Closed container is just saying we can apply our closed law for the first law of thermodynamics for closed systems. Nitrogen is given its properties, and we know that this is at 25 Celsius and 100 kilopascals. So fully defined, right? Nitrogen is an ideal gas, as you know, N2. It's in the form of a molecule with two nitrogen atoms, and we have two properties, which means this is fully defined. The tank has a total volume of 4 meters cubed, so note that we have within these 4 meters cubed, 5 kilograms are occupied by water, and the rest is nitrogen because it's a gas. And an additional 500 kilograms of water is slowly forced into the tank. It can be assumed that the temperature remains constant, so therefore this is an isothermic process, right? So no change, isothermal process, no change in temperature. And we are to calculate the final pressure. So this is what we're looking for. Final pressure of the nitrogen. The work done during the process, from 1 to 2. The change in internal energy from 1 to 2 for the gas, so for nitrogen as well. And the heat transferred. Okay, so let's think about what's going on here. We have a container, as per usual. It's a closed system container. This is a bit different because it has a way for us to put water in. So let's just put a little kind of syringe kind of thing going on here. Okay. And, part of it is occupied by water. I'm not sure how much. I know that's 500 kilograms, and the rest is nitrogen. Okay, and then what we're going to do is we're going to use this syringe to put more water into the system, right? And then when we do that, what will happen is, let me grab this. What will happen is we will increase the amount of water, right? So we can say maybe water, this is not going to work. Like so, there you go. Maybe water comes to this level now. Okay, so that's what the problem statement is telling us. What do we know? We know two properties of this nitrogen. We know that it is at 100 kilopascals. And we also know it is at 25 Celsius, right? So ideal gas, I can go ahead and transform this into 298 Kelvin, because if I need to do any math with this, I know I need Kelvin. And then what do I know about this other side here? Well, I know the temperature should be the same, right? It's the same 25 or 298 because it's an isothermal process. And I also know I don't know the pressure per se, but I know pressure 2 in this case, state 2, is greater than pressure 1, right? So it's greater than, which is 100. So I know pressure 2 is more than 100 kilopascals. Why? Because I'm literally compressing this nitrogen with the water that's being squeezed into this tank. Okay. What about the water? What do we know about the water? We know the water is at 25 degrees Celsius, and we know we have 500 kilograms of it. And over here, we know it's still at 25 degrees Celsius because the temperature did not change in this process. And now we've added another 500, so we end up with 1,000. Cool. So what do we need to do here? We need to find the pressure 2. So this is straightforward, right? Pressure 2 is straightforward because we know this is an ideal gas. So therefore, PV equals mRT. We know there's no change in mass for the nitrogen. So therefore, P1 V1 T1 has to be equal to P2 V2 T2. And we also know the temperatures are the same. T1 T2 are the same. So therefore, both 25 or 298. So therefore, we know that P2, which is what we're looking for, is just going to be P1 V1 divided by V2. So this is easy to begin solving the problem. Now what we need is the ratio between the volumes. Okay, note, and this is important, this is an equation for an ideal gas. So this is exclusively for the nitrogen, right? This is not for the water. So, and often what students do at this point here is they say, oh, this is 1 because the volume is 4 meters cubed on both cases. No, this volume here is not any volume. This is the volume of the nitrogen, right? As is this pressure. This is the pressure for the nitrogen, and this is also pressure for the nitrogen there. Okay, so the question is, what is the volume of the nitrogen 1 and 2? And we know, right, we know that this guy here has a total volume of 4 meters cubed, the total thing, right, this area, this volume inside here. We also know that whatever is not occupied by water is occupied by nitrogen. So I can say with confidence that the volume 1 of nitrogen will be equal to the volume total, right, the 4, minus the volume occupied by the water. Okay, and I happen to know the volume occupied by the water because, you know, I know the temperature the water is sitting at, and I can also go ahead and calculate the specific volume for the water, right, using my thermodynamic tables, because this is a property that is well known. So in other words, what I'm saying is that if I want to find V1, I can just do my 4 meters cubed minus the volume of water H2 in state 1. Okay, and if I want to find in state 2, then same thing, copy paste, right? It's just going to be the nitrogen, the same 4, that does not change, minus the volume occupied by the water in state 2. Okay, so to find out what's the volume of the water, which is what I'm missing now, I can just do, I know that the specific volume was just the volume divided by the mass. If I know the mass, I can find the volume, right? The volume is just going to be the specific volume times the mass. This I know to be 500 on state 1 and 1,000 on state 2, by the way. 1,000 on state 2. And this I can grab off the property tables, which I know UNSW likes to use Rogers. So this is just a quick, this is blurry. It's just a quick snapshot of the property tables, and I'm looking for 25, so I'm over here, and I'm looking for a specific volume. You can't really see, this is not very, I hope this would be a bit better quality, but let me read it off my computer because this probably has a better quality here. Give me a second. Interesting, my computer, it's pretty good quality. Okay, so this is 0.01030. Okay, that's the number there at 25, and that's the number I'm going to grab. 0.0010003. If you ever go to look at this table, you're going to see that this is actually 0.1, right? Not 000, but there's a 10 to the minus 2 there. So that's why we have the 2 extra zeros. This is something that also throws students off. Okay, so what I know is that this will be 0.12003 times 500. And unit-wise, what I'm doing is I'm multiplying meters cubed per kilogram by kilograms, meaning this ends up being meters cubed. Right, so the volume of water on state 1 ends up being, what did I get? 1 second, I need to go back. 0.5015 meters cubed. Okay, oops, I was down here, my bad. Okay, and for state 2, that's just going to be literally double that, right? So 1.003 meters cubed. Okay.